Year 11s, we are going to look at the information you need to know about electromagnets now. So as I go through this, you'll want to make notes. You might want to pause the video, watch it 2 or 3 times so that you're sure you've got everything. So you've already looked at what happens if you have a single wire. With a single wire, the magnetic field is a circle around it. And we can find out the direction by using our right hand, putting the thumb in the direction of the current. Sometimes you might have situations where the wire is going into the page like this, in which case you might have 2 symbols. You might have a circle with a cross in it. This means the current is going into the page. And if it's a circle with a dot in, the current is out of the page. So that means coming towards you. How can you remember this? Well, if you think about it like an arrow, if you saw the arrow coming towards you, you'd see the tip of the arrow. If you saw the arrow going away from you, you'd see the feathers of the arrow as a cross. But we're going to look at electromagnets now. So electromagnets are magnets that you can turn on and off depending on whether you have current flowing or not. So what are they made of? So electromagnets are really, really simple. What we do is we have a coil of wire, and if it's a coil of wire, it has a fancy name. It's called a solenoid. That just means coil of wire. And if we connect it into a circuit like this so that current flows, then we produce a magnetic field and we've produced an electromagnet. So electromagnetic, or just electromagnet, if current flows. If we disconnect the battery, it is no longer a magnet. So what does the field look like? Well, it looks a bit like a bar magnet, and you know what a bar magnet looks like. It looks like this. And what direction is the field? Well, the field always goes north to south. This is going to be a north pole. This is going to be a south pole. I'll talk about how you can remember that in a second. So the arrows are going to go north to south. What else can we label about this? Where is the field the strongest? The field is the strongest where the lines are closest together, and it's the weakest where the lines are really far apart. So much weaker out here, much weaker out here. What else do we need to know? So you need to know the direction, and it's very simple to work out the direction. You use the same method you do for this. So it's the right hand rule. You put the right hand in the direction the current is going. So what we need to do is label the current. So it's going positive to negative. So the current is going like this. Okay, and so on. So now we get our fingers and we put them in the direction the current's going. So the current is going this way. So the current is going like round this way. And then our thumb points in the direction of the North Pole. So it's really simple. Right hand rule for this. Thumb goes where the current's going. The fingers show you the magnetic field. For a solenoid, you put your fingers where the current is, and your thumb tells you where the North Pole is. There's nothing more to it than that. We also need to know, how can we make an electromagnet stronger? And this comes up all the time. So there's 3 ways we can do this. We can increase the current, So we would have a bigger potential difference from the battery, which would create more current. Do make sure you mention current though. We can also increase the number of coils, so more coils equals a stronger magnetic field, or we can add an iron core. So instead of just having a solenoid on its own, what we can actually do is we can add a piece of metal inside it, specifically a piece of iron, all right, as a core, and this will make it stronger. If you want to understand why it makes it stronger, we'll think back to the lesson before half term. Iron can be magnetized by a magnetic field. It can turn into a induced magnet. So we've got the magnetic field from the solenoid plus the magnetic field from the induced magnet in the iron core. They add together and they make the field stronger. Okay, I've got one final thing for you to do. So you don't need to make a note of this. You don't need to write anything down, but just have a look at this picture and just think about how the bell is actually going to work. They could ask you in an exam to explain what is going on here. I'll give you a second to pause the video and think about what's going on. So what's the process here? Well, at the moment the switch is empty, there is no current flowing, the electromagnet is off. If we close the switch, current will flow through the electromagnet. That will create a magnetic field around the magnet. The magnetic field will attract this iron arm towards the electromagnet, and that will do two things. This circle here will hit the gong and make a noise, and as the arm pivots, it will break the circuit here. So now we've got a circuit that's open, current will not flow, the electromagnet will turn off, and the metal arm will go back to its original position. Now we've completed the circuit again, the current will flow, the electromagnet will turn on, it will attract the metal arm will hit the gong, and then it will break the circuit. This process will repeat again and again and again, and we will hear the bell go on and on and on and on. But like I said, you don't need to make a note of this. It's just one possible application of electromagnet.